So let's do the next bit here, programming languages. We're going to talk about at least 3 different layers of languages. First generation languages, second generation languages, and third generation languages. I suppose we could refer to other languages other than that. We don't really talk too much about object-oriented languages. We sort of stop here talking about high-level languages, which are third generation languages. So let's see what we got. Okay, so supposing, and notice we got some little notes here on the recipes. So let's say we had a recipe. We've got some ingredients. I guess that'd kind of be like the data, and we've got some instructions. So that could be kind of like a program, right? We have data and we have instructions. Recipes like a program, has ingredients and instructions. Ingredients kind of be like data. Yeah, all right. Recipes are easy for humans, but it would be hard for a computer. So I think the point here about a recipe that you have in your recipe book for a computer is this idea of ambiguity. Computers require very precise and accurate instructions to work. If you just said to a computer, crack an egg and cook it, right? You have to be much more precise. You'd have to say, pick up egg, move to the right, proceed, move to the pan, crack. You'd have to be very exact, even to the details of how far you're moving and how fast you're moving and all of that stuff. Whereas a human, you just say, pick up the egg and crack it in the pan, right? For us, we have a lot of ambiguity that we are tolerant of, whereas computers are not tolerant of ambiguity. I want to define the word ambiguity now. Ambiguity is where we see something and it could have more than one meaning. It could have multiple meanings. And so it's that, run to the car kind of thing, right? Well, which car, how are you going to run, how far, what speed, etc. Whereas with a computer, you'd have to remove all of those ambiguities. Otherwise, it doesn't work. So that's what we mean by the specific instructions and the ambiguities. Now, we've got 2 slides that work together here, slides 3 and 4, and they are there for us to sort of consider this idea of ambiguity. So, I mean, here we have, it's supposed to, I think, be like the legend of Arthur. I don't know if you're familiar with the legend of Arthur, but actually the legend of Arthur was preceded by a Greek legend like 2,000 years ago, where something similar. But this one here, Arthur, and the Greek legend was, there was a sword stuck in a tree, and whoever could pull the sword out would be the king, right? In the Arthur legend, it was a sword was stuck in a rock, and if he could remove the rock, the key from the sword from the rock, he would be the king. Only the king could do that. What Arthur doesn't notice, or whoever is here doesn't notice, is there's a lot of dead remains of dead people around the rock. Correct. And the swords, so in the Arthur legend, there was a sword that had a name. It could do all kinds of magic stuff. What it does here is it impales whoever pulls it out onto the rock. That's not so bad. So great. So I guess that explains all the skeletal remains around the side of the rock. Yeah. Yeah. And as I said, if you went back and looked at Greek mythology, you would find that there was a legend which was very similar. Okay, so now the thing is, here we have some words. Once upon a time, a man found a sword in a stone. He thought that it would be like Excalibur, and hence he tried to, and eventually he succeeded in pulling it out of the stone. However, the sudden pullback was so strong that he ended up tripping and falling, and the sword went through him. Now, these 2 slides basically tell the same story, right? They tell the same story. And the idea that we're supposed to give you by looking at the same story being told in more than one way is the fact that we can represent algorithms, where an algorithm is a step-by-step instructions to solve a problem. Algorithms don't have to be on computers, but they could be. Algorithms can be used. No, you can't put an algorithm on a computer. You have to translate it into a computer language. But the algorithm could be used as a basis to get a computer language problem solved. Now, the idea being that that algorithm can be represented in more than one way. We could represent an algorithm with images, or we could represent an algorithm with story written like they did here. So here we represented a step-by-step sort of happening by images, and we represented it with a story. You can do the same with computer algorithms. And the point here is made that that story could be represented in more than one speaking language, right? If you tell the story, you could tell it in English, you could tell it in Arabic, you could tell it in German or something like that. It could, and it would still be the same story, but with a different way of representing it. And you could do it in a comic strip, or you could do it some other way. So we need to define this term, which is algorithm. What does it mean? And I've just said it's step-by-step way to solve a problem, or here is saying a process or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. Now, just like above, we can represent a story in more than one way. We can represent an algorithm in more than one way. We can represent an algorithm as just plain English, where we just write and say what we're going to do. We could represent it in pseudocode, which is very similar to plain English. Pseudocode is just a little bit more formal than plain English. You need to have a begin and an end, and you need to put things indented if they're dependent on something else. So we have just a little bit of structure to it. Or we could use a flow chart, which is graphical and has its own set of rules. So, for example, in this slide, we have an algorithm which is represented in two ways. On the left is represented by a flow chart, and each of these symbols here has a meaning. So if you have a symbol which is got rounded edges like that, that's a connector which is used to start and end a page of a flow chart, and then you could use that to point to another page. So we've got a start and an end, and they're of that type. Then we have this one with the do you call that a rhombus? Whatever, it's a four-sided, but it's not a rectangle. So that is for input and output. And so here we have some input, which is being represented by that symbol. And we have some other input that's represented by a similar symbol. Then we have a proper rectangle, which rectangle having a right angle, that is used for our processes. So we got a process there where we're calculating pay based on the inputs. We don't output anything. All right. And so the same exact process, the same algorithm is shown in pseudocode. So just like this had a start and an end, pseudocode has a beginning and an end, and then it just explains what's going to happen at each of those things. Okay, and so pseudocode is not a computer program, but it could easily be converted by somebody who knew how to write a computer program into a computer program. And so that's pseudocode. Now, yeah. Next one there, program code. So when we write it in a computer language, and there's lots of computer languages that we can use, then we can call that program code. And so programming language is formal, has, when we say a string is what we call a word in computing. All right, so computers can't work with the algorithm by themselves. They need to have it explained to them in a computing language. So because computers only work with zeros and ones. When we put something into a computer language, we actually, what we've got is we've got associated with that computer language, we have a way of converting it to zeros and ones instructions. Okay, and so that's what we do. Somebody has gone to a lot of trouble, a lot of computing to produce this thing which will either interpret or compile whatever you've written in this computer language into a bunch of zeros and ones that the computer can understand. And so that's why our computing language is kind of special in that. And so this slide is supposed to represent, and I'm sorry about the small stuff up here because I wanted you to have to see the notes underneath. And again, as I said, all of these notes are on D2L. So what we have here is we have if we had our simplest way of programming something, a binary program is all that the computer can understand. And what we have with a binary program is we say, okay, where is the instruction or the data, and what is it, right? And so this is saying at the first at 0 location, which is actually the first location, we have this instruction or data. Now, the thing beside it is a hexaprogram. The hexaprogram actually has the same information as the binary program, but it's just represented in a way that's a little more compressed, I suppose. So there's no real difference between these two in terms of what the computer is understanding there. Now, in the next row, we've got our second generation or second level programming language, which would be our assembler language or assembly. And so what's happened here is we have some special assembly instructions, which basically still have to refer to a particular location. But then we have instructions there that have almost readable, right? So we can see there's a load, LDA, we've got to add, which adds things together. SDA, which is to store. So we've got something there where we're sort of writing programs that are almost understandable by people. That's that assembly language programming. And here we can see it here, some assembly language instructions. And what do they mean? A level higher than that would be our third generation or higher level languages, and they would include things like C, Pascal, BASIC, Python, Java. And what they do is they have very sort of programmer centric, I guess what I'd say. What I mean by that is that it's written in a very formal way, but it's written by the programmer in a way that they can understand, right? So the programmer understands that this is declaring a variable called a, which is an integer variable. Well, actually, all of these are integer variables. There's a variable a, and a value has been set for it, which is 83. B has been set with a value of 23, and C. All three of those are integers because they're all in the same line of code. And then the next line of code, the integer C takes the value of whatever was in A plus B. So that would be in the C programming language. Now, Python programming language is here, so that's maybe a higher level programming language. It's even easier to use. And Python is also a object-oriented language. So with Python, you can use classes and methods and objects. C, not so much. There is a C# that you can, C++. Now, if you look at the Python program, it's easier to use. We didn't have to say what type of variable we're going to use. We just say A is a number 85. The Python programming compiler or interpreter is complex enough that it's able to see that the number 85 is an integer. So A will be an integer just because it's 85. And then it does the calculation as well. Is there anything that I missed from this? Yeah, there's a bunch of stuff there. There's a video that you can watch. I'm not going to show you that video now. I'm just going to sort of point to you. As I said, that's all on the so if there's the notes on lecture 4 are where there's a lot of notes, right? And so there's some video links in there that you can watch. How does a CPU work and that type of thing. So there's lots for you to do at home. I mean, you don't have to start. I'm trying to make it easier for you, right? There's lots of stuff for you to do at home. You don't have to go and search and find stuff or read a textbook or anything. It's all here on the D2L. Just follow those notes, watch the videos when you're feeling a bit bored, and hey, you should be. I'm hoping then you'll feel like you're ready for the quiz. So yeah, there's some other languages. What do I need to say? Yeah, I haven't mentioned those other languages. Ruby on Rails, PHP. Yeah, PHP is used to, if you want to work on the internet, everything's on the internet now, right? We program stuff to work, apps on our phones, but every one of those apps, not everyone, almost all of those apps on the phone work by connecting to some server somewhere. right? So you need to go through the internet. If you're going to work through the internet, you have to have some programming languages that will work with that. So we use HTML, and we use JavaScript, and we use PHP. So PHP is important because it allows you to using your HTML that you're programming with some PHP code in there, you're able to communicate with a database on a server somewhere. So that's kind of important because on our websites now we have all kinds of databases working, right? We're shopping. That's, every one of those shopping sites has a database which records all of their customers, all of their stuff, all the transactions that occur. So PHP is really, really good and important. Ruby, I'm not as familiar with, but I think it's working a little bit with artificial intelligence. So with artificial intelligence, you're going to make big data sets, and with those data sets, you're going to find the patterns that exist in those data sets. Yeah, so we have these two different ideas of interpreted and compiled. An interpreted programming language, what we're doing is we're reading one line of code at a time, and we're executing that line as we go. With a compiled programming language, we take the whole program, we convert it to machine code, which is a bunch of zeros and ones, which is going to make a smaller, more compact thing, and then we run that. Now, the benefit of having a compiled program is you can give to somebody your compiled program in the form of an exe or a .com file, and they're not able to mess with it. All right, unless they've got some way of doing a reverse compiler and sort of pulling out from the hex code that's in there, they're not able to actually see what is the program. So that's good. That's what people want. I mean, if you're like you're Microsoft and you've got an operating system, you don't want people to take the bits of your operating system and reproduce them and sell them. So the only stuff that you give people is compiled code, right? You don't give them what we call the object code. We don't give them that because we don't want them to mess with it and steal it and do other bad things. All right, so Python's really good, and there's some reasons that it's really good. It's easier to start with. Python has a lot of really, really good tools in it. So you might at some point do an operating systems course here. So I think operating systems courses are being done by software and hardware students. When you do that, you'll find that you'll be programming in Python using a library, which allows you to sort of work at the operating system level. Pretty cool. So Python is used like that. It depends on the libraries that are available as well, right? So there are libraries now available with Python, which will allow you to program switches and routers on a network. So it's nice. It's a nice programming language, and it is object oriented. So with Python, you can create objects and have classes and methods with them. You'll learn more about that later. I mean, we introduce programming using Python here at the college, and so you might have 2 or 3 Python courses. Python, the other programming that you'll be doing if you're doing a programming strand or programming degree is you'll do a lot of programming in JavaScript, and because JavaScript allows you to change things on a web page based on user input. And so JavaScript and Python actually can be used with HTML. So you can use them, you can build web pages, and you can use JavaScript and Python with them. Yeah, okay, so yeah. Low-level languages, they are languages which were in the first slides. So your low-level, your first generation, second generation language assembly. So the problem with your low-level language is as it says here, it might be specific to a particular CPU. So if you write a programming language that works on this type of computer, it might not work on that kind of computer, right? Whereas your higher level languages, they tend to work, they interface with an operating system, and they can interface with many operating systems. So assembly or assembler language, that's only going to work on one type of computer. You're going to have a different assembler for every different type of computer. And lastly, our high-level languages. As I said, there's a difference between interpreted and compiled. I've already discussed that, haven't I? Yeah, high-level languages. Since the COBOL would have been one of the first high-level languages, COBOL and Fortran. Fortran was a engineering, scientific, mathematical language that was introduced in the 1950s. COBOL was a business language introduced in the 1950s. And we talked about that in the previous week, right? So the thing about our languages, the higher level languages, they are easier for people to read and work with. Interpreted versus compiled, interpreted language, you're going to distribute the code, which is going to be readable. But that means that people would be able to change it. All right. And the other thing is it's going to work one line at a time. Whereas compiled language, you're going to distribute just the compiled hexadecimal code, which people cannot read. And so that's going to run faster. It's going to take less time, but it's going to take more work to develop it. And it's going to be more secure. And so there's some, so there's these points here, right? Loosely typed and strongly typed language. So C is a strongly typed language, which means that every time you declare a variable, you have to say what type it is. So for example, is it an integer? Is it a float? Is it a string? Is it a character? Is it Boolean? You have to say when you declare it. That's strongly typed. Whereas Python is not strongly typed. With Python, you just declare the variable. As soon as you assign a value to it, it picks up what type of variable it should store there. And the other thing about Python, and you can do this with Java also, is you can change the data type. You can cast it. We call it casting. So you can have a data type which is a string, and you can change to a integer with Python. Python's pretty cool. So I mean, don't feel bad that you're learning in Python. It's a good language to learn on. And there's some other programming languages that you might come across. JavaScript, PHP. Java is kind of being replaced by Python nowadays, I think. But Java would do a lot of the stuff that Python would do. It's a little bit harder to write because you have to sort of set things up a little bit more lines of code. C++ is like the C programming language, but works with objects. R and Ruby on Rails, I've never used them, but I think they're used for big data and artificial intelligence. What does it say here about them? Doesn't say anything. All right, so that's all we have for today. I hope that's okay. If you have any questions,